We're looking at section 3.5 today, but before we get started, here's a warm-up. Take a second to do this to check your understanding of some of our previous learning. All right, so there are two things that need to be done on this warm-up. The first is that we need to check these two solutions and make sure that they really are solutions. So we check their second derivatives, we plug those into the differential equation on the left side, and we see that we get 0 for y1. And now we do the same for y2, find its first and its second derivative, substitute those into the differential equation to obtain, again, 0. So both of them are solutions, but now it remains to still be shown that these are linearly independent solutions. So we use the Wronskian here, loading in the two functions in the first row and their derivatives in the second row. We take the determinant, and for values of x greater than 0, we have that this is not 0. And therefore, these are solutions, and they are also linearly independent. And now let's get into our lesson for today. Today we're going to take a look at section 3.5, the method of reduction of order. And the goal, of course, the title says it all, is to take a second order equation and turn it into a first order equation and use techniques from our prior learning to solve. So just a few ideas as we get started. Just think about where we are. We've showed already how to solve a second order linear differential equation, homogeneous, with constant coefficients. Imagine that p and that q are not functions, but imagine that they are they're constants. If we showed how to do that, right, in our first day of this unit. But let's think about how the fact that this is becomes a little bit of a trickier problem if those are not constants. So we're going to slightly, as we continue to do throughout this course, we're going to broaden once again the set of differential equations that we can find solutions to using various techniques. Finding solutions to these kinds of equations can be much more difficult than finding solutions to differential equations with constant coefficients. So our goal today is to at least to see if we can come up with a technique for solving this kind of equation. And now here's the catch. With the method of reduction of order, and this might not seem very powerful at first, but we have to give you one of the solutions. If we know one solution, we're going to be able to use this method to reduce the order and find a second solution. We kind of skated over the details of this when we mentioned double roots in our first day of this chapter, when we were solving second order equations with constant coefficients. And now we're going to be able to justify that with more rigor. Here's how we're going to do it. This is the magic. And honestly, this is like the only instruction you kind of really need. If you have one solution, we're going to multiply that by v. And that's going to generate a second solution for us, I guess. Well, we'll see. We'll give it a try here. Now, it's important to keep in mind that v, as we move forward, v is a function. V is not a constant. So we'll see. Again, you just kind of trust me on this, but let's see what happens with that choice. So let's solve one, and then we'll kind of go back and dissect this and think about this in a more general context. So here's our differential equation, x squared y double prime minus 4xy prime plus 4y equals 0 for positive x. We're given one of the solutions up there. It says given that the first solution is y equals x. Can we come up with a second solution? Yeah, so that's the goal here. So we're going to take the q that I just mentioned a second ago. We're going to let y equal v times x. So v times whatever the first solution is. It won't always be v times x. In this case, x happens to be one of the solutions that was given, though. We're going to try and come up with a second solution here. So the first thing we're going to do is, I think you can probably guess where we're going with this. We're going to try and substitute this into the differential equation. So we need y. We need y prime. Notice the use of the product rule here because v and x are both functions of x. So we have v prime times x plus v times the derivative of x, which is just 1. We also are going to need the second derivative. So I've already kind of done a little bit of algebra here, right? But if you take the product rule of the previous expression, y prime, think about it. You're going to get v double prime times x, product rule. But you're also going to get v prime out of that. And then from the v, you're also going to get a v prime. So do you see where the 2v prime is coming from? I didn't show my work very well there. I apologize. Now substituting those in, y double prime and y prime and y, where they go in the original differential equation, that should satisfy the differential equation. And now let's look for something in particular. With this choice, I think you're going to notice that something nice happens. Do you notice that all the terms that just have a v cancel out? I'm not looking at the terms that have a v prime or a v double prime involved. But take a look at this. Don't you see that there's a negative 4x here times v? And over here, a 4 times vx. Those are going to cancel out. And there's nothing special about this. In every problem where we're doing this method, that should happen. And so what we have here is an equation that just has v double prime and v prime and no v in it. Okay, maybe that doesn't sound very significant yet. But let's clean this up and see if we can figure out what we have here. Dividing through by x cubed and just highlighting the v double prime and v prime. This all looks a lot like something of a nature that we had in the last unit. And so, well, it almost looks like a linear first order equation, doesn't it? Except there's kind of like an extra prime here and here, right? If we could just kind of erase those, that would be nice. Well, we kind of can do that. We're going to make the substitution w equals v prime. Now, don't let this lowercase w be confused with the Wronskian. We're using this just because it's the next letter in the alphabet. So making that substitution, well, then I guess we have what we want. We have a first order equation. Here it is. This is the title of the lesson. This is us reducing the order of the equation. So isn't that nice? And that little differential equation is one that's quite feasible. You guys all know how to solve that using a couple different methods. I'm going to use separation of variables. But basically any first order equation you know how to handle. So you could also use an integrating factor there. So I'm just separating variables. I will kind of skate over the details since you've done this before. And I apologize, there's a little bit of a fast and loose change of constants happening here. You can see that C2 on that previous line is not the same C2 as it's on the next line. We're doing some e to the stuff there. So we get w. We also want to remember, though, here at the end here, I've got equals v prime, just to remind myself that like w is not what we kind of went in the rabbit hole, and now we've got to come back out. What was w again? Oh yeah, that's right. W was v prime. So now to recover v prime, we can integrate, or excuse me, to recover v. And notice that introduces a second constant. Well, that's actually kind of what we want. You'll see here. And now we want to as we come back out of this rabbit hole, we want to remind ourselves that v is also not really what we want. W wasn't what we wanted. V wasn't what we want. These were all kind of temporary tools for us. Really what we wanted was this second solution. We started by saying let y equal v times x. And so now I'm just multiplying the thing I just said by x. And notice that I've kind of absorbed the 1/3 into that constant there. Now, again, another moment of playing fast and loose with the constants. I apologize. Okay, so let's multiply that out, and we're going to see something that looks familiar here. C1 times x. That part is not a shock to us. But this part right here, that part is new. And so there it is. There's the general solution. We've got a second linearly independent solution using one solution that was given, and then the method of reduction of order to kind of pull this cool trick. That's pretty cool. So now let's talk about kind of the general principle behind this. And we'll also develop a formula that can maybe get this for us all the time. Oh, sorry, a summary statement for you there. On these next slides, you can just relax, you can enjoy until the formula comes. You can take notes if you like, but I just mainly wanted to kind of show you how the formula is derived. So let's get into it. All right, so that's why the popcorn's on the slide. You can just get your popcorn out if you want to. So the goal, we've already said, is to reduce a second to a first order differential equation, and we're going to start by letting y equals v times y1, which is, we're going to suppose, is a solution that's been given to us. We're going to find y prime, very similar to what we did before. Y prime times y1 plus v times y1 prime, which is just the product rule, and y double prime. Now things were really nice when we had an x, but it's not too much worse here too. Again, we get this like doubling of this term in the middle. So y double prime is what you see before you, right? Just using kind of two instances of the product rule and combining like terms. Okay, so now, again, you know the play we're going to make. We're going to make those substitutions for y double prime, y prime, and y in the original differential equation. Apologize about that stray mark there. So making those substitutions gives us those things. And again, we should have something goes away here, right? This is kind of what we said was just always going to happen with the reduction of order method. If we collect the v terms, and again, I've already scratched it off there, you saw, but that's the part that's going to go away. So let's take a look at it. If we collect the terms that have a v, that's that. The color coding is a little much, Mr. Chase. I apologize. V, the teal one, right? You can look at all the terms that have a v on them. Y1 double prime, we've got one of those. We've got a p times y1 prime. That's going to be part of our stuff that's multiplied by v. And then last, q times y1. And now look at that. Now why can I just slash that off? Why is that going to go away? Well, the answer is because we know that y1 is a solution to the differential equation. And the differential equation right here, if you plug y1 into it, gives you 0 on the right side because it's a solution. And so that's, look at that. It's exactly what, what we have here. That stuff in the parentheses just is that exact situation. And if it's really a solution, that should come out to be 0. That comes out to be 0. And so now the equation that we were just looking at, this equation right here, if that part goes away, has that property that we wanted. We've got like a v double prime and a v prime, but there isn't a v in the equation. So now we are able to do this reduction of order that we like to do. We're going to let w equal v prime, taking a q from what we already did. And when we do that, we get the following. You can see that we're using, again, just separation of variables. Honestly, this parallels pretty well what we already did in the last example. So the work here is fairly straightforward. We're just doing separation of variables, and now we're integrating. We get a natural log on both sides. Hopefully you can see the use of the chain rule right here. Integrating this is kind of interesting, right? Because this is the integral of this is going to be the natural log of y1. There's going to be a 2 there as well, minus 2. And the derivative, if check this with the chain rule. Isn't this going to be, if you take the derivative of this, 1 over y1? Oh wait, times y1 prime. So that is that derivative that we want. And the rest I think is straightforward. We have an integral in there. We don't know what p is, so we can't take the integral, but whatever it is, we'll take the integral of it. So now this is where we're at. We can do a little bit of algebra to obtain this, and you can see that e to the natural log of y1 to the negative second, we can pull that part up using just properties of exponents. We kind of separate some of these things. And so e to the c, let's rename that c. E to the natural log of y1 to the negative second, we'll just, by properties of exponents and logs, that'll all cancel out. We're going to get by the inverse property, and we'll just get y1 to the negative second there. That's this part. So that explains where this came from and this came from, and then this is just the other part that we have here. And so now we have, that's what w is. Now we want to remember that that's v prime, and so to integrate that will give us v. So I know we've got an integral inside of another integral in there, I apologize. But I think we're really close now, because v, remember, is what we want. We just want, for y2, we're just going to do v, which we have a formula for now, times y1. And there it is. This is, again, you didn't have to take notes on all of that, but here it is finally in a box. And you can see that y2 is equal to, and you can just kind of run this formula. I'll show you one example of how to run this formula in a minute. There's one important thing to notice that ties in a very nice way back to the lesson that we just did. That numerator inside that integrand there, that numerator is the Wronskian times a constant, but we already have a constant out front. Remember, the Wronskian we don't know for an equation down to the constant. We just know that it's some multiple of e to the negative integral of p of t dt. So that is, though, the Wronskian. We've already got a constant out front. So that's kind of a nice way to remember it even more compactly if you already have your Abel's formula memorized. Let's try this now. You can use, honestly, just every single time if you want. You can kind of work through the details the same exact way we did the first time. You don't need the formula ever, actually. So feel free to do that. You could just not remember the formula. But I do think the formula is pretty handy here. So let's give it a try here. And we'll, one thing I should have shown maybe first on this is p of t here, remember, is obtained by first dividing through this whole equation by 2t squared. So this p of t will actually be 3/2 t to the negative first. So that's what you're seeing here. I apologize. Okay. And then t to the negative first is the solution that's being given. So that's going to appear here in the denominator. I'm just using that formula that was on the last slide. Hopefully you wrote it down. And it appears as here as well. And so this is like just what we get. And now we just have to work out the details. There are a few details to work out. If we integrate that numerator in there, that power of e, excuse me, we'll get negative 3/2 ln t, and using properties of exponents, we get t to the negative 3/2, and subtracting exponents, we have that as our integrand. And now integrating that gives 2/3 t to the 3/2, really plus a constant, right? We have really, I've kind of ignored the constant in all this, by the way. There really should be kind of a constant out front here times all this, right? But I'm just trying to get another fundamental solution. Don't worry, I'll make sure to add the constants we need. So we get t to the 1/2 when we multiply there times a constant. So here's our final solution. We figured out, I mean, we knew t to the negative first was a solution because it was given when we started. But now we have a second fundamental solution. We're ready to write the general solution. There it is in a box. So, okay, so if you permit yourself to use this magic little formula, the method of reduction of order, although that might sound fancy and it's quite a process, you know, we do have a nice formula for it. So I'm giving you permission to use that formula, but I do want you to know, as always, where this stuff comes from so that you could derive this pretty quickly. I'm going to show you one more method for this too, which I think you're going to like. Take a look at this. Here's another method, and you're welcome to use this instead of or whenever you feel like it. This is kind of fun. And honestly, I really thought about just teaching this method because it follows so nicely from what we did yesterday. So the first thing we're going to do, we're solving the same equation we just did. So we got p of t is 3/2 t to the negative first. And now I'm going to use the formula from yesterday that we learned for the Wronskian, Abel's formula. So here we go. The Wronskian is apparently c e to the negative integral of p of t dt. So here I go. C t to the negative 3/2 is what we get. Now why am I doing that? Well, we have a second function that we're still looking for. And apparently, this is the Wronskian for the function we know, t to the negative first, and the function we don't know, which we don't know. But when you do that and you like load them into the matrix, apparently you get, see, notice what I'm doing. I'm loading t to the negative first, but then for the other solution, I'm just like loading y, because I don't know what it is. I'm just like y and y prime. But apparently blue is equal to red, because we just said we kind of have two ways of writing down the Wronskian now. We can actually like compute it directly using the determinant. We also have this formula in red, and those should be the same. Well, that gives us a way of solving for y, the second unknown function. What do you think? I think you might like this. I'm going to kind of put it in its canonical form right now, although you might be able to figure out how to do these without having to use a proper integrating factor or separation of variables. But I think this works pretty well for an integrating factor. Now that we have it in this form, we can see the integrating factor is going to be e to the integral of t to the negative first dt, which comes out to just t when you work out the details. So I'm multiplying through by t, and you can see that just right away, that's going to work, right? We've got t, and we've got the derivative of t, which is 1 on the y here. So that's what we're looking for. Is this really the derivative of a product of t and y? Yeah, it is, right? It's a pretty simple product rule. So now we're integrating. Notice that we like generate in that process a second constant. And I've absorbed the constant that goes with this, right? Normally you'd be like 2/3. Well, it's all in that constant, right? We'll go with it. That's what t times y is. Of course, we need to still get y. But there it is. We're done. Notice that even in that process, we didn't have to, we just kind of divided through by t, and we just kind of got the solution. I've renamed some constants there, by the way. C1 is now, oh well, whatever. There's stuff and there's stuff, so go with it. So I thought you might like that additional technique. Honestly, maybe it's a good way. It's really not a bad way to do it. It's pretty compact. The work is quick, and it doesn't involve memorizing another formula. If you already have the formula for the Wronskian memorized, then maybe you just go with this method. Feel free to do this instead if you like. They are provably the same. All right, well, I want to give you one opportunity to practice as we finish, so I'm not going to put up the work for this, but let's see if you can't get the answer. Oh, no, sorry. I apologize. I'm going to show you one important connection back to what we talked about earlier. Here we go. This is the thing we talked about. This is the double root situation. So let's proceed to solve this as if we didn't know what we're supposed to do when we see a double root. Let's try. This is a second order linear homogeneous differential equation with constant coefficients. So we can try, we'll try y equals e to the rx. And when we do, we'll have this as our characteristic equation. Yeah, we're proceeding as normal. We're going to factor it, and we can see that the only root is r equals -4, which gives this c1 e to the -4x solution. And we kind of maybe know what's going to happen here, but certainly not. The answer is not c1 e to the -4x plus c2 e to the -4x. That's not, those are not linearly independent solutions. You know, those c1 and c2 could be collapsed. So we kind of need a second linearly independent solution. And so we're going to proceed to use this solution that we just got and see if we can generate another solution. Let's see if it agrees with some of the thoughts we already had about how to handle the double root situation. So I'll just use the technique we just learned a second ago using the Wronskian, just to show off that method. So we get c e to the -8x as our Wronskian. Notice that our function p of t here is simply 8. That makes that pretty easy. And then we also compute the Wronskian using the second method, right, where we don't know what y and y prime are. And then we set the blue and red equal to each other. And we've got a little tiny differential equation there. I'm going to multiply through by e to the -8x. When I do, see the constant just remains, appears on the right side. I'm calling it C2, if you're okay with that. And what we have on the left side is the product rule for e to the 4x and y. Now we integrate. I'm producing, as I do that, another constant, and then I divide through by e to the 4x. And so what I get is, again, one term that is not a surprise, c1 e to the -4x. But the second term, c2x e to the -4x, is the cool part, right? That's the new part. That's the second linearly independent solution, and what we have now is the general solution. So I like that because we kind of made mention of the fact that in the first unit, the first section of this chapter, the first day, I mentioned that this is how you can kind of handle the double root situation, but I kind of did some hand waving. I said, just believe me. And now you can see why that happens. We need that second linearly independent solution, and we also have, with the method of direction of order, a way to get it. Really cool. So that kind of establishes in a rigorous way what we said earlier. I'm going to give you one more opportunity to practice here. I'm not going to go through the details, but take a second to pause the video and work through the details of this. And you'll see at the bottom I already have the solution, so you can cover it up or something like that and see if you can but I don't have any of the work showing, so feel free to take a minute and see if you can't land that problem. We've given you one solution, and we got a differential equation, and it's not meant to be any majorly more tricky than what we've already done here today. You can use either of the methods we talked about. It does look maybe a little different at first, though, with just an x plus 1. There's a way in which we talked about 3 methods today, really. One way is just to like kind of noodle your way through it. Let y equal v times y1, whatever your given solution is, and then just kind of follow the consequences of that, and then what needs to happen will happen. The other way is to use the secret formula, which is nice. It's pretty nice, compact, easy, quick. But then, of course, you have to remember it. And then we also learned this third method using the Wronskian. So whichever you like best, feel free to use any of those methods you like. Thanks for your attention, and we've got some additional resources in the slides. If you take a look, you're welcome to poke around and learn some more on the internet. All right, you guys, have a good one.